on pseudorandom generators for read-once branching programs in any order. This is a work by Michael Forbes and Xander Kelly, and Xander will be giving the talk.
Hi, thanks. Okay, yeah, so this is a joint work with my advisor, Michael Forbes. Okay, so before I get into the background, here's just a quick look at the main result. So we show that there is an explicit pseudorandom generator with polylogarithmic seed length for read-once log space computations. And then sort of the main point is that unlike previous constructions, our generator works even if its output bits are read in any arbitrary order. So for the construction, we use the bounded independence plus noise framework recently introduced by Haramidi, Lee, and Viola. And then something I want to highlight is that our proof is Fourier analytic, but somehow we do without needing any Fourier tailbound for the class of functions we're trying to fool. So if you're familiar with past works on pseudorandom generators for restricted function classes, this might be surprising. However, it seems that our techniques are still compatible with Fourier tailbounds. So specifically, if we plug in this recently derived tailbound for constant width branching programs, we can get our seed length down to nearly log squared n in the constant width case. Okay. So a pseudorandom generator for a class of Boolean functions is just a map that produces strings that look random to every test in the class. So specifically, we say that G epsilon fools the class if for every test in the class, we have that the expectation under strings generated by G is close to the expectation under truly random inputs to F. Okay. And some reason we're interested in pseudorandom generators is that if you can get pseudorandom generators with small seed length that fool some class of algorithms, this gives a natural generic approach for achieving de-randomized versions of those algorithms. And as an example, in the 90s, Nissan gave a pseudorandom generator with seed length log squared n that fools log space algorithms. And then something we'd really like to do is to improve this seed length to order log n, and this would resolve the RL versus L question. So that is, it would be sufficient to show that any problem solvable in randomized log space, you could actually just solve it with deterministic log space. Okay. So here is a picture of a read-once branching program. A read-once branching program is basically just a finite state machine where the transition map is allowed to be different at every step. So how you evaluate one of these is you begin at this start state, and each vertex has two outgoing edges into the next layer, labeled with a 0 and a 1. And we just read the bits one at a time and follow the corresponding edge until we get to the last layer. We end up somewhere in this last layer. And then we can say branching program defines a Boolean function. We say f is equal to 1 if x defines a path that takes you from the start state to the accept state, and 0 otherwise. And then also, the number of states in each layer is called the width. So this is an example of a width 4 branching program. And then, OK, why are we interested in these? So polynomial width branching programs are a nice way to capture and reason about log space computation. OK, so here are some examples of branching programs. The AND function on n bits and the parity function on n bits have very efficient branching programs just with width 2. So here's a picture of those. And then in contrast, the inner product function over F2 doesn't have an efficient read-once branching program in the natural order where you read the bits of x first and then you read the bits of y. So a simple communication argument can tell you that when you're halfway through this program, you essentially need to remember everything about x, which means you need exponential width at that point. However, this notion of the best width you can get for a specific function, it's sensitive to the order in which you read the bits. So the inner product function does have a small read once branching program. If we read them in this alternative order where we're interleaving x and y, we read x1 and y1. So here's a picture of a width4 branching program that implements that. Okay, so now I'll talk about some previous constructions of pseudorandom generators for branching programs. So there are various constructions that achieve this log squared and seed length. And I want to highlight a common high-level approach that they all take. It'll be somewhat vague, but I would say in each case they rely on some sort of communication argument. So a natural way to get a small seed length generator is, you're going to invest some randomness to generate the input for the first half of your program. What you want to do is reuse most of that randomness to generate the second half of the input. Okay, so then you need to argue that that's okay. What I mean is you need to argue that the branching program cannot tell that you're doing that. So why can't it tell? Well, when you evaluate it and you're halfway through the branching program, the only thing the program can remember about the first half of the input is encoded by which state you reach in the middle layer. So if there are only a few states, then it can only remember a little bit about this first half of the input, so you should be safe to reuse most of the randomness again to generate the second half. Okay, so just something to point out is obviously this strategy for developing pseudorandom generators for small space only makes sense if you know the order that the branching program is going to read your bits. So even more than that, we actually know that Nissan's generator fails to fool branching programs if they read its output bits in some different order than you were planning on. So Nissan's generator does not work in any order. Okay, so there's been some feeling that this paradigm used by these three constructions we just talked about are somehow stuck at this log squared and seed length barrier. So if you want to get a better seed length and eventually maybe to RL equals L, maybe we need some new techniques. So you could say as a vague challenge, okay, construct a pseudorandom generator for small space that's not like these. That's not very concrete. So you could try to capture that challenge more concretely as follows. So construct a PRG that produces pseudorandom output strings that look random to read once branching programs, even if they're read in any arbitrary order, x pi 1, x pi 2 to x pi n. Okay, so here's some progress on this question. A recent line of work on the constant width case of this question established a PRG with polylogarithmic seed length, at least when w is constant. And previously, the best known result for general width was this seed length that's no better than square root n. And so we get a seed length that has log cube dependence on n and logarithmic dependence on the width. So here is the main theorem stated somewhat more precisely. The rest of the talk will go over the proof. So like I said, the construction is this bounded independence plus noise construction from HLV 17. And what are the ingredients for this construction? It's actually very simple. We're just going to use a bunch of copies of KY's independent distributions and combine them in some way. And then for the analysis, we're going to show that we can write any branching program as this small sum of simple functions phi I, and just argue that each of these functions are fooled by our generator. So onto the construction. Like I said, our only ingredient we need is KY's independence. So a distribution is KY's independent if it fools K local tests. So those are functions depending only on K input bits. And it actually fools them exactly. So the expectation under your KY's independent distribution is exactly equal to your expectation under the uniform distribution. And something relevant for us is that KY's independence can be efficiently sampled at the price of K times log n truly random bits. Okay, so I said the construction is recursive. We let the base G0 just be a KY's independent distribution, And then this is how we recursively define GI. So what's going on here is DI and TY are just KY's independent distributions. And then we're combining TI with this recursive GI minus 1 with a bitwise and then we're combining the resulting vector with DI using a bitwise XOR, or addition over F2. Okay, so, and then the output of our PRG is just going to be GR for some R. And since we have R rounds of recursion, and each time we're paying for D and T, then the total number of random bits we use is like R times K times log N. And in the analysis, we'll see we need to set R and K to be like log N, so that's why we get log cubed N. Okay, so just to summarize, this is our construction we have. We have G is equal to D plus T ANDed with a recursive copy of G. So how do we analyze this? We analyze it with a sort of recursive hybrid argument. So it goes like this. We're going to kind of inductively assume that G prime looks random to read once branching programs. So if that's true, then G looks like D plus T ANDed with the uniform distribution to read once branching programs. And then, so this idea is sort of standard. Our main technical contribution now is to show that this distribution D plus T and U fools branching programs. Okay. So as a warm-up to that, we can see pretty easily why this distribution D plus T and U fools parity functions, which is certainly necessary since they have small width branching programs. So how do we see that? We can compute this expectation of the parity function. It turns into this product here. Let's try to understand this part on the right first. So this expectation over U is just going to be equal to 0 or 1, depending on this event. So whether or not alpha and T is the all 0 vector. Okay. So now that we have this expression, we want to show that the error is small. We do that with a case analysis on the Hamming weight of alpha. So if the Hamming weight of alpha is small, if it's less than K, then this parity function is just a K local test. So it's fooled exactly by D, by our KY's independent distribution. So we get an error of 0. Okay, so on the other hand, if the Hamming weight of alpha is large, it's larger than K, then the larger the Hamming weight of alpha, the rarer this event becomes. So in particular, if the Hamming weight is at least K, then this event happens with, at most, probability 1/2 to the K. So in either case, we get this error for parity functions. Okay, so more generally, we can show that the distribution D plus T and U fools this kind of function I'll call K products. So let F and G just be any arbitrary functions that depend on disjoint sets of input bits. And then we're going to define H to be the degree K part of F. So what's happening here? We take the Fourier expansion of F, and then we keep only the degree K terms, so we throw away everything else. So keeping the degree K terms, that's what we define as H. And then the claim is that D plus T and U fools the K product phi, which is the product of H and G. Okay. So we'll get to see at least a sketch of this proof. So what is the first move is we observe that we can push the expectation over the uniform distribution inside this product. So that's because it's uniform, it's independent on all of its coordinates. Certainly that's not true of D and T, so we can't push those inside the product, but we will need to. So now we're just going to consider the square of this expression. We use Jensen's inequality to pull out D and T. And then we observe this part is at most 1, so we just forget about it. And then, okay, so what's happening here is we've arrived here, and now it's very, very important that U is, once we've arrived here, inside of the square and not outside. But once you've arrived here, you just do some standard Fourier analytic calculations to see that this is at most 1/2 to the k. So the point of all this is d plus tnu fools k products. Okay, so how do we finish the proof? I'm going to claim that we can take any branching program and write it as this decomposition. So unfortunately, probably not time to see how we get to this, but I promise that there's some reason why, there's some simple way that you would arrive at such an expansion. Just can't talk about it now. But what is this saying? So mu is just the mean of f under the uniform distribution, so it's just a number. L of f is the low degree part of the Fourier expansion of f. And then we have a sum over all the vertices in the program. They have some k product associated to them. Okay. So then why does that help us? Well, we fool the low degree part exactly. So that's taken care of by just d, the k-wise independent distribution. So we get no error on the low degree part. And then we can compute this difference between our expectation and the true expectation. It's bounded by the error we get for every k product. And then the total number of vertices is nw, and this is how much error we get on each k product. And then, to get overall error epsilon, we need to take k to be like log nw over epsilon. Okay, so that's the whole proof. So what did we do? We got a pseudorandom generator with polylogarithmic seed length for read-once branching programs, and it works in any order. And so our construction was this bounded independence plus noise construction. The analysis, first we made this recursive argument, and then we have a branching program decomposition, and then d plus tnu fools k product. So I guess I have second, I should say that the reason it works in any order is because permuting the bits of a k-wise independent distribution just gives you a k-wise independent distribution. So there's no problem with that. So, okay, that's all I have. Thank you.
Questions?
Can you say something why you have NW, like your decomposition of NW terms, right?
So we were getting a term for each vertex. I guess the point is that we had to consider programs, subprograms, that go to V and come from V. So sorry, maybe that's not so clear. So you could define subprograms of your branching program by having the same start vertex and then picking some other vertex to be the end vertex, right? Okay, so that's what we're doing there.
But why, I mean, if it's not like too much, why do you need that?
What do you mean?
Why do you need to go to every, why do you need to count over all the products?
So I guess, I mean, to get this, what's really happening here, I mean, there's details suppressed, but this is just collecting all the terms of the Fourier expansion of f in different places, okay? So somehow we just see that we can organize them in a way that this is what we get, and that's good enough, I guess.
So just to comment on that, these results are very nice. The definition of this as read-once branching program is actually something that's been common in the pseudorandom generators area, but it is not the general definition of read-once branching program, which is normally oblivious
Sure.
read-once branching program.
Yeah.
So this decomposition is not in general correct for read-once branching programs overall, but for oblivious read-once branching programs, also known as OBEDs. So, I mean, in general, with applications, very often it doesn't matter, but if you're going to, in terms of some of the applications, in terms of, simulating finite, space-bounded computation, it's not as critical, but as a decomposition for read-once branching programs, technically, it's a different law, it's a more restricted model
Sure.
that you're dealing with.
Uh-huh.
So that may be, I'm wondering whether that's some of the confusion, but
Okay.
anyway, it'd be nice if
Sorry?
There's a variant of the descent generator works to give like a fixed list of branching programs, not all of them. Is there like any variant here if I give you like a list of read once branching programs, not all of them simultaneously that use the logic thing?
I'm sorry, so you're saying this is like a more general model, or I didn't quite understand?
There's if instead of pulling them all of them, you just have to pull like a given list of them.
Thinking like the RL and SC.
Yeah. Is there a way to
You're saying of different orders, or?
Yes.
Oh. Okay, so, and then what's the question?
Is there a way to get a smaller seed length for that, you know, if you don't need to pull them all?
Oh, I mean, at least not from what we're doing. I mean, we're not really. I mean, the reason it works in any order is just because we use k-wise independence. So I don't know if you could try to define some other distribution that sort of worked like k-wise independence, but weaker in that sense, like that you could deal with just a small number of orderings you could have, but I would say definitely not immediately from what we have.
So the methodology for proving the RL equals alpha, it suffices to have a PRG for read once branching programs in a particular order.
Yes, that's true. So.
Is there anything that getting one for arbitrary orders, like does it have some?
So is there any concrete reason? So like I said, one of the biggest reasons people are interested in this was just the challenge, like do something new, right? So I guess that was like, that's why people in the area care about it. But I could say there's one concrete thing, maybe I should go back. So like this situation we talked about here. So more generally, you can say that a read once formula has so of polynomial size, say, has a polynomial width read once branching program in some order. Maybe not in the natural order, but in some order, right? So we get the first black box PRG for read once formulas. Does that make, okay.
All right, let's thank the speaker then.